Hello! Welcome back to Organic Chemistry, and welcome to Organic Chemistry Part 2. I just want to start with a little review about what we saw at the end of Organic Chemistry 1. We saw SN1 and SN2 reactions, where a halogen is replaced by something else, say an OH-. And this could happen all in one step, which would be an SN2 reaction. Or it could happen by way of a carbocation intermediate, in which case it would be an SN1 reaction. So that was ochem 1. At the beginning of ochem 2 here, we're going to see kind of a reverse reaction. Now we are starting with a molecule with a hydroxyl group, and we're trying to substitute a halogen for that hydroxyl group. The problem is that it isn't too easy to get the OH off. So the first thing that has to be done is to activate the OH. So we're going to add something else to the oxygen. This activation of a hydroxyl group is one of the central points of this chapter. Something pretty simple and basic you can do is to add an acid. Well, I guess it's not basic if you're adding an acid. Get it? That was a little acid and bases joke. But anyway, this is what happens if you add acid. I put the hydronium ion down here, but you can think of it simply as H+ if you want. The electron pair from the oxygen here is attracted to a hydrogen, and now our oxygen has a positive formal charge and it is activated. Being activated makes this a much better leaving group, because this can happen. The oxygen, having a positive formal charge, really doesn't mind taking the electrons in this bond for itself. And once oxygen grabs those electrons, it forms a water as the OHH separates from the molecule. And the molecule which lost those two electrons from here, it ends up with a positive charge here, so we formed a carbocation. And with that carbocation formed, it's really easy for a halide to come attack and form a bond to that positively charged carbon. Notice that this is an SN1 reaction, because we're substituting one group for another and we're going through a carbocation intermediate. We have done this as an SN1 reaction because a secondary carbocation is formed, which is fairly stable, more stable than a primary carbocation. If the OH was bonded to a primary carbon, then we would run this through an SN2 reaction mechanism, and it would look like this. Here I've put the hydroxyl group on a primary carbon. So we're starting with a primary alcohol. And note that it gets activated similarly. And then, after activated, the bromide attacks at the same time as the water is released in this step. And that forms exactly the same product, but in one step. What we just looked at was a method to add, substitute a bromide onto a molecule using an acid. So what we just used was HBr, hydrobromic acid. And I said that using acid to activate a hydroxyl group is the simplest way to do it, but not the best way. There's more than one way to boil an egg. If we activate the hydroxyl group with a bigger molecule, we can get better yields and maybe even avoid carbocation rearrangements. Another thing that's used is phosphorus tribromide. Here the electron pair in the oxygen is attracted to the phosphorus, a bond is formed with the phosphorus, and a bromide is kicked off. And I've kind of skipped the part where the pyridine solvent takes the hydrogen off of the oxygen. We're going to get right to the exciting part, where the bromide that we created attacks the carbon and this group leaves. And that forms the same product. Something very similar can be done with thionyl chloride. The thionyl chloride activates the OH. Again, I'm skipping over the part where the pyridine removes the hydrogen from the oxygen. And we have created a group that will leave when a chloride attacks. So this group goes bye-bye. And again, we're making a very similar product, only in this case a chlorine gets added instead of a bromine. Okay, let's look at one more way to activate the alcohol. This beast is called para-toluene sulfonyl chloride. And when it activates an alcohol, it really activates the alcohol. This gargantuan beast is a very good leaving group. This right here. So good that pretty much any nucleophile can attack this carbon and this group will leave. Here is a nucleophile attacking that carbon, and here is this group leaving. And this is what we formed, and this is the very stable leaving group that has left. The end, for now.